Okay, so for those of you that maybe struggle a little bit running the PowerPoint and seeing everything, this is the video, and also you get to enjoy a little bit of my explanation, or not. So let's have a look. How did we discover the structure of the atom? Well, radioactivity and the structure of the atom are very closely related. One of the most famous scientists was Henry Becquerel, who discovered this strange property of some materials that would affect photographic film, because we know that nowadays that there's some elements that give out radiation. They're radioactive, and one of the ways of detecting radiation is by photographic film. Other famous scientists that worked on this were Marie Curie and her husband. Now, in radioactive atoms, the nucleus is not stable, and it will break down, or it will decay is a better word in physics, and when it does that, it gives out a particle or waves of radiation, and then it will become a more stable atom. Okay, and this process we call radioactivity or radioactive decay, which is what this topic is all about. And early experiments with this radioactivity led us to find out what the structure of the atom is. So we know that everything is made of atoms. This is not a new idea. The ancient Greeks came up with this idea at first. In some substances, for example gold, aluminium, copper, the element is made up of atoms which are all of the same type. So a pure gold ring, is made up of only gold atoms. And recently we have developed microscopes that are powerful enough to see individual atoms, even work with individual atoms. But up until very recently, this was not possible, and we couldn't actually see the atom by itself. So how do we know it exists? The first idea, Greek, Democritus, came up with the idea that everything was made up of tiny little individual components, which he thought of being like balls. And the idea of the atom being like a sphere or a ball is what we've taught you in Key Stage 3. Coffee. So, ideas about how the atoms work and how structure works has changed over time. In 1803, John Dalton came up with the idea again that everything was made of atoms, and reaffirmed it. And he explained that these atoms were little like spheres that could not be split up. And in fact, he had the wonderful idea that an atom was like a circle like this, and the way it joined with other atoms was with like hooks, and each atom would join to other ones by hooking onto neighbouring atoms. Okay, which is a very good idea. It's not exactly how things work, but it's one way of seeing things which is quite appropriate. So let's get rid of my stuff there. So he also suggested that not only were things made up of atoms, but elements in chemistry, were made up of identical, the same atoms, which is correct today. Now, 1897, J.J. Thomson discovered tiny little particles with a negative electrical charge, and he guesses what they were called. They eventually got called electrons. J.J. Thomson was a very famous scientist, worked at the University of Cambridge, and his son went on to come up with some even better ideas. G.J. Thomson, that contradicted his father's research. So you can imagine the Christmas dinners were quite fun. So these negative particles were given out by some atoms, and they were much smaller than the atoms themselves. So then we started to realise that an atom was not a perfect sphere, that it was actually made up of maybe something else. So this was the electron that Thomson had discovered. It didn't quite fit in with the way Dalton had seen things and Dalton's model of the atom. So Thomson came up with a new model of an atom, which was a little bit strange. He decided that the atom was more like a sphere that was positively charged with negative electrons blobbed about inside it, and it became known as the plum pudding model because electrons are thought to be like raisins inside a plum pudding. The pudding is the positive sponge and the electrons were the raisins in the plum pudding. Okay, which is a strange idea, but it did explain the existence of electrons, but it didn't quite fit in with everything else. So he was one of the great scientists. This guy worked in one of the most important universities and most important cities known to mankind, otherwise known as Manchester, Ernest Rutherford. And he came up with what's called the nuclear model of the atom, which is what we use nowadays still. So what he does, he came from New Zealand, went to work with J.J. Thomson in the University of Cambridge, worked on the plum pudding model, and then whilst he was working with uranium, he found a different kind of radiation. So he called these radiations alpha and beta, alpha and beta, not one was better than the other. That's a physics joke, by the way, you should laugh at that point. So alpha and beta radiation, and he discovered some of their properties. Now, Rutherford started to work with another scientist, and they discovered that an element, radium, gave off radiation, and as it does that, it turns into something else. So Rutherford explained that when atoms or elements gave off radiation, it must be bits of the atom that are being given away and given out, and they become a smaller atom afterwards. So one element changes into another element, which is what the ancient alchemists wanted to do. They wanted to turn lead into gold, but unfortunately that wasn't the change that was happening. There was other changes, for like thorium and into lead. So Rutherford became Professor of Physics at University of Manchester, and two of his assistants, Hans Geiger and Ernest Marsden, did an experiment to see if radiation, these particles or bits of atom, could be reflected back. And they found that a gold bit of foil could reflect some of these particles. So Rutherford was quite shocked. He'd imagined that this was like an artillery shell, a big bit of atom being given off, and it was bouncing off a bit of something thin like tissue paper. So he came up with the idea that the atom wasn't solid, that there was actually empty space, and I'll explain the experiment that led him to this in a second. He won the Nobel Prize in 1908, and he was knighted in 1914, so this is one of the greatest discoveries that we've ever made. So the experiment with the gold foil, how did it work? So let's have a look at this. We had a thin sheet of gold foil here and a lead box that had an alpha radiation source. Now this lead box had a hole in it so that the alpha radiation was given out in like a beam of particles. Okay, any alpha radiation given out by the radioactive source and hitting the lead would be absorbed by the lead. So this made a thin beam of radiation. You put the gold foil, and nowadays in the video that I've attached from the guy from CERN, they have a radiation detector. What the Geiger and Marsden had to do is they had to take a little bit sheet of phosphorus film that glowed when a particle of radiation, alpha radiation, hit the film, and they had to sit in a very dark room for hours at a time holding this little bit of phosphorus film in different positions and counting how many times it flashed. And they spent weeks at a time in this darkened room gathering the data of this experiment for hours and hours at a time. I think that's otherwise known as torture. So, in the experiment, okay, if we place the detector, for example, here, okay, and we test, we would see that we will get loads of detections, loads of alpha particles will hit the detector and go straight through this bit of gold foil. Okay. If we move it into a position that is a bit off to one side, a bit of an angle, and we run this test, we start to see that every now and again this particle, an alpha particle, would go through the gold foil but be deflected. It would change direction. Okay, and if we put it in position 3 and run the test, and we wait and we're very, very patient, every so often, not a lot, an alpha particle will actually bounce back off the gold foil. Okay, so how did Rutherford reach his conclusions? Well, what he decided was that most alpha particles would go straight through the gold foil and not be deflected. The reasons why I'll explain now. A few particles would be slightly deflected, and then very, very few would bounce straight back. So all of this was carried out in a glass dome in a vacuum, because alpha particles will, in just a few centimeters of air, they will strike particles of gas in the air, and they will be absorbed by these particles and they'll be stopped. So alpha radiation won't travel very far through air. So you had to make a glass dome with a vacuum with this alpha particle source with a bit of gold foil, and then the phosphorus film that was a detector had to be placed in different positions. And so one of the biggest and most important things that Rutherford had was a very, very, very good laboratory assistant that could make all this apparatus out of glass. So he became one of the most famous laboratory assistants, but unfortunately, of course, nobody remembers his name. We only remember Rutherford. So how did Rutherford explain that some of these alpha particles bounce back? It wasn't what he was expecting to see, because a plum pudding model couldn't give a proper explanation of why a few particles bounce back. So Rutherford calculated and came up with the nuclear model of the atom. These calculations actually led him, now we know, to an answer that was very, very close to the real size of the nucleus of the atom. So he suggested that the atom was mostly empty space, a tiny, tiny, tiny nucleus in the center, and most of the mass is here, and then around the outside, electrons orbiting or going around this nucleus at a distance, as if it was like the sun and planets going around the sun. And if you were to have the nucleus, for example, in a tennis court, it would be the size of a pea, and the electrons would be just specks of dust outside the tennis court, hundreds of meters away. So how did his explanation fit the results from the experiment? So if we look at most of the alpha particles passing through the gold foil, most of the atom is empty space, okay? A little bit like the brain of a year 11 student. So most of them pass straight through without hitting anything, and these get detected on the other side. A few come very close, like this one here, and get deflected off in another direction. Okay, let's just go back and replay that. So that this one gets deflected off and gets detected at an angle, and very, very, very few will actually hit the nucleus dead on and bounce back. So here Rutherford decided that the nucleus must have a positive charge, and the positive charge repels the positive charge that the alpha particle has. Therefore, when an alpha particle comes close to the nucleus, it gets deflected, it changes direction. And then because the nucleus is so massive, there's so much mass here, when an alpha particle hits it, the nucleus doesn't move, but the alpha particle bounces off, like a tennis ball hitting a wall. So now, an exercise at the end, I want you to do this in Google Forms. So I'll set this up in Google Forms. Each statement fits either the plum pudding model or the nuclear model. Okay, we now know the nuclear model is the correct one and the plum pudding is incorrect, but we're not talking about correct and incorrect. What we're talking about, which of the statements fits each of the models. Okay, so can you do that in Google Forms for me? And then we'll get on to doing more radioactivity stuff. Okay.